Hello everyone, good afternoon. Welcome to Samvaad. We are resuming after some time, a few weeks gap, and now we are going to start a talk series which is being presented on behalf of SIG Automotive. And therefore, there is going to be a series of 5 talks about which Professor Roland will speak in a bit. And this is the first of those 5 talks. So to chair today's session, we have our colleague, Professor Sujit Rao. Sujit Rao works on robotics. He's one of the associate professors here, and he works on robotics and controls and many other areas. And he also takes interest, he has a background in automotive himself. And without further delay, let me hand over the mic to Sujit to introduce the talk and the speakers. Thank you.
Thanks, Sujit. Yeah, so it's my pleasure to chair this session. So there are 3 parts to today's talk, all by our colleagues at the Institute, Roland, Sujit, and Vivek. So Roland will be talking about automotive electronics and software, Sujit on automotive software engineering, and finally Vivek on security engineering in the automotive sector. So the first speaker, Professor Roland Haas, he's an adjunct faculty member here at IIIT-Bangalore. He comes with over 25 years of professional experience, both at the technology and the managerial levels. He used to head Daimler India, which has now become, I think, Mercedes-Benz Research. He's also co-authored several papers, several books and papers, and the recent one is a textbook on automotive connectivity and cybersecurity. He's also founded the company by the name of QSO Technologies. The second speaker, Professor Sujit, he's an associate professor here. His research interests are in the domains of software engineering, formal verification, programming languages, and so on. He's also published several research papers, and he's involved in technology transfer and consultancy as well. Final speaker, my colleague, Professor Vivek. He's currently the Infosys Foundation Career Development Chair Professor. He was previously a postdoc in the cryptography group at the University of Bristol in the UK. He served as an editorial board member of several journals, and he was also a recipient of the DST's Inspire Faculty Award. His primary research interests are countermeasures against side channel attacks and homomorphic encryption schemes. And I'd like to also say that I worked with all of them in some capacity or the other over the last few years. So yeah, over to you guys. Roland, I think, is the first speaker, right? Thanks.
Yeah. Sajid, thank you so much for the kind introduction. I would like to start with the first part of the presentation. Before that, also to give you a few words on the special interest group Automotive, and then an overview of what we are planning in this area. So welcome again to today's Samvaad-Talk. We talk about a very interesting topic, how the automotive domain is changing, emerging platform for cybersecurity, computer science, IT, and innovation. And we'll first look at the special interest group Automotive that is coordinated by me and Professor Sujit. The Automotive Special Interest Group is a club of professors and topics that are related to the automotive domain. Here you see the current members of this group. It is spanning a wide area of different areas. Professor Sujit had given a kind introduction. You just met him in the introductory part. We have Professor Srinivas, for example, who is also our dean in R&D, who is interested in Web3, semantic models, and also autonomous driving, data management, a huge area of different things, from radar to control systems to software to artificial intelligence deployed in this domain. Some of the projects which we're working on, you see there's one topic like virtual product creation for electric cars, then the domain of electric cars in terms, for example, of computational challenges for routing, charging, and path planning. There are quite a bit of things that are related to the cybersecurity aspect of automotive, for example, also on the Tara Hara platforms. We do have projects in smart cities. The IUDX platform is a big project together with Indian Institute of Science that IIITB is involved in. And then, of course, we also look at the overall topic of sustainable mobility and the ESG objectives. That is a common theme that we have. Today's talk is the first of a series of 5 talks in the automotive Samvaad-Talk domain, which starts today and will end in middle of November. We have a talk that is coming up on software-defined vehicles, a term that you will hear in many discussions in the automotive domain. That's given by Mr. Ramesh, General Motors R&D. We have a speaker from Ericsson in Sweden, Satyam Dwivedi. He will talk on 3GPP network-based positioning. We do have a talk on digital twins for engineering, so a little different perspective on how simulation models actually contribute to the virtual product engineering in the automotive domain, which has come very, very far. And finally, we have again a speaker from IIITB, that is Mrs. Jaya, Professor Jaya, who is talking about extracting geometry to understand the data from the automotive environment. With that, I would like to go now into our first talk, and I handle the first part. We talk about automotive electronics and software and the trends and challenges in this field. The automotive industry is changing very fast, and many talk about digital transformation to summarize what is changing there. Let's look at it in a little bit more detail. Since about a decade or so, there has been these 4 areas that have been the drivers. Connectivity, so enabled typically through the GSM network, autonomy, so putting driver assistance to the next level, so to enable self-driving cars, and we see the first robo-taxis on the road. You might have heard about the experiment by Cruise in San Francisco that actually now has a paid service, so people really pay for it, for robo-taxi, no driver anymore, that takes you from one point to the other in San Francisco. And San Francisco might not be the easiest place to drive around. Fog in the summertime, very narrow roads, up and down. So let's see how this experiment will go. Shared mobility has been there also for some time. What is meant is not only ownership of a car, but you would like to share the car and the mobile device so that you have better cost and efficiency. And there are many experiments in this area also going on. And then, of course, electric cars. This is a topic of the hour. Electromobility. We do see a major shift in many regions, many countries towards electric cars because of zero emission drive within the cities. And a lot of possibilities that are there to have electric cars as part of a overall holistic mobility concept in the future. But there are many other points that are also important. We have an increased share of software. We also look at that a little bit more in one of the other slides. We have high performance computing platforms and vehicle computers. This is really a new topic because a car has been a mechatronic device that was defined by control structures that had to be working in hard real-time environments, but the bandwidth was rather low in terms of the data-driven points. But with infotainment and other things, this has changed. So now they have high performance computing in cars. Also means that we have a cloud integration because some functions in the future do not only run on the vehicle itself, they're actually in the cloud and they interact with the vehicle software stack. And that has been there since the pandemic, and still, we see the aftermath of that. This is disrupted supply chains. And that means that, the supply chains have to completely, adapt to new situations. There has been a lot of delay in chip, for example, delivery to the automotive OEMs, has led to the situation that some had to produce cars that were not completely ready. And later on, some devices were installed because the chips were just not ready. We see that startups drive the innovation. Also, this is something more than a decade long. The startup scene brings in a lot of ideas to the automotive OEMs and they try to engage the startups in an early phase. And finally, what's also very interesting to see, the roles changed and the borderline between OEMs and suppliers, first tiers until end tiers, has changed. Suddenly OEMs sell you a complete chassis stack, like what you see here in terms of Volkswagen with an MEB electrification kit, and others like Bosch will offer a car in the future. Who knows? So these things really change dramatically. As I said, software plays a fundamental role, and this means that we see a very rapid increase in software. Steadily, that has been there over many years, but now pushed by infotainment and more so by the self-driving functionality of cars, we see that we really break into new complexity levels where we can maybe see a billion lines of code of software, not only on the car, but also interacting in the cloud. And that is a completely different complexity level than we talk about. Infotainment is also driving this, and you see here one hyperscreen and a Mercedes EQS, that is a luxury segment for battery electric vehicles and Mercedes. And you see it looks more like a computer screen with all sorts of devices. You have, of course, the instrument cluster digital, you have a middle console, and you have also for the passenger side, the screens. You can imagine that this needs a lot of computing power to visualize it. And more so, you will have more and very, sophisticated features of augmented reality that also play a role here. So this system really needs a lot of computing power. How does it actually translate into the evolution of EE architectures? So starting with the first thing that has been there about 20 years ago, and then, steadily increasing, is a system of connected embedded control units connected to bus systems like CAN and LIN. And with each new function, you had a new embedded control system. So it grew in size and numbers. Then the idea came up, let's design a software stack like AutoSAR, the open architecture for software systems and cars, and also map different functions to embedded control units. It doesn't make sense to only have one dedicated ECU per function. So several can run on an embedded control unit, and then you connect the different bus systems or gateways. The next evolution step was to define domain controllers. The domain could be chassis, powertrain, or driver assistant. These domain controllers coordinate a few embedded control units that are dedicated to those functions, and the bandwidth was increased. So we needed systems like NFD, flexible data rate, that allows you to transfer much higher bandwidths on the network in the car, as well as automotive Ethernet that goes into the giga bandwidth area. So you could transfer much more data, and domain controllers were actually being the gatekeepers for the different subfunctions. But today, we see an architecture that again fundamentally changed. We have high performance computing devices or vehicle computers in the terminology of Bosch. These devices are as powerful as the most powerful desktop PCs. They are, not running a classical computing device, CPU, but also have GPUs on board. They are number crunching devices. They are connected to the cloud. And then you still have the mechatronic domain, where you have embedded control units in single ways that are connected to that. But this architecture is a fundamental shift, because now you have this classical ICT domain with high computing devices and the mechatronic-driven domain with the embedded control units and the classic network architecture there, and both has to come together and work together. That is the challenge here. Finally, what are we up to in the future? I think that fundamentally the self-driving features of cars, which you might not see in the individual cars and passenger cars so much, but in the shared mobility domain because of the cost. But that is fundamentally really a shift. And you see the different levels here, nicely depicted by, the green, the blue boxes. the driver has to do less, the computer takes in up more functionality. And the interesting thing is where we are right now here in the level 3 domain is where certain things can be done by the computer, the car in its self-driving device, but still the human passenger, the human driver has to oversee certain things. This area is very complex because handing over to the machine and handing back from the machine to the driver is something where a lot of errors can happen, and which is not so easy to do. In the future, we will see the full level 4 and 5, the robotaxis. Here, the corner cases, the edge cases are really the challenge. 99% of the time things are clear, but this 1% that is really the concern, where the system goes into unknown terrain and has to drive safely. This needs a lot of more electronics and software, and that's the theme of our today's talk. With that, I would like to hand over now to our next speaker, who will talk about the domain from a different perspective.
Thank you, Professor Roland. This is Sujit here, and I'm the second speaker of the day. I'm going to focus on a particular aspect of today's topic, which is automotive software, and I'm going to focus on the engineering aspect of it. So automotive software engineering is the topic of my part of the talk. So let me proceed. So I will be talking about three things here. After introducing the idea, I will briefly talk about some current trends and the challenges to software engineers that these trends are going to pose, and then how the work that we are doing as a part of our research contributes or may contribute to handling those challenges. These are the things that I'm going to talk in the next 20 minutes or so. So in a single slide, what are the various properties of automotive software? As Roland's introduction nicely portrayed, we have seen that these much of the software is invisible because it is really hidden from eyes. You do not see it running on, let's say, a computer monitor or something like that. There are real-time constraint imposed on these software systems because they are, if they do not meet those deadlines, then it will be considered a failure of a feature, which could eventually lead to catastrophic consequences. And because of those catastrophic consequences, which we do not want, all these software systems largely can be classified as safety critical. Now, cars are increasingly interconnected. They are connected with each other. They are connected with the cloud. So the car has been a computing device on wheels for a long time, but it used to be an isolated, self-contained system for a long time, but now no more the case. It is heavily interconnected, and therefore all sorts of security concerns are there. They are liable to cyber attacks. And the third part of our talk today is going to deal with some important aspects in that particular part. As Roland spoke, we are already approaching 1 billion lines. So undoubtedly very large software systems, very complex. On top of that, to make things more interesting, they are all loosely coupled. They are supplied by many third parties. Well, this is nothing new to automotive software, but the thing is they are also safety critical. So we have been having this in mobile devices or ERP software for a long time, but often, you know, if the mobile software stops, nobody gets killed, but that's not the case with automotive software. And then increasingly with autonomous driving, we have ML AI components inside that. We have heavy concurrency in our automotive software, where multiple ECUs, between 50 to 100 of them are running interacting software components. and therefore concurrency is unavoidable. Similarly, elements of distributedness and interconnectedness are also there. So in short, this particular thing summarizes all these topics. It's a large and complex domain, software domain, and therefore poses very, very steep challenges to the current software engineering innovations and practices. So with that, let us see what the industry is trying to do in order to handle these particular challenges or properties. And I will spend very little time on this also. So what are the trends that we see today? So one of the trends that you see is there is a major shift towards model-driven approaches or model-driven engineering approaches, where engineers use high-level languages instead of low-level programming languages like C. Similarly, why do they want to do that? Because they want to verify the correctness of the systems they are developing as early as possible. So upstream verification is the name of the game today. And this also ensures that we often generate the code automatically, so that the questions of low-level programming errors are altogether eschewed. And this also makes it possible to comply by various standards. And the second major trend is that of standards. Okay, so people are trying to avoid practices which have unnecessary variabilities. We try to stick to standard practices, standard rules, standard procedures as far as possible, standard templates. And while there may be many dimensions to how standards are getting imposed in software development, I talk of three of them here. One is in the software architecture, the other is how software coding is done, and finally some other software in terms of the various concerns. So let's look at AUTOSAR, which is an software architectural standard. It is basically the automotive open system architecture. It was introduced in 2003 and was done by more than 150 global partners. And various things were, various high-level architectural details were standardized with enough amount of leeway for individual implementers to use their creativity and customization and improvisations. But by and large, these standardizations actually fostered plenty of interoperability and interconnectivity. So here is the AUTOSAR software architecture diagram. While there are plenty of details that we can talk about, I want to draw your attention to the three-layered structure here. This is the first layer, the application layer. This is the basic software layer. And finally, we have the hardware layer. ECU stands for Electronic Control Unit. And this kind of mimics the systems that we, the good old Unix operating system kind of thing, where we have the application layer, the kernel layer, and the hardware. In the same manner, we have something like that. And each of the subsystems, be it the communication or be it the ECU library, the operating system, all these are standardized to a certain extent. That is the important part of it. The second is a coding standard called MISRA C. Okay, this is a C++ standard. And the idea is to ensure that programmers, if programming is done, they follow coding standards. And also, if we use MDE or model-driven engineering and prefer automated code generation, then the code generators abide by certain standards, which is MISRA C standard in doing so. And this also helps implementation, development of many static analysis tools, and many of them are already highly used by automotive software engineers. This is from MathWorks, right? Like that. So here is an example of what is not MISRA C compliant. So as you can see here, this particular array is being initialized in this particular way. So this auto increment operator has a side effect on X, and X is also being used to initialize the second element of this particular array. As you can imagine, C does not stipulate the order in which the elements of an array are initialized. Therefore, depending upon the compiler or the underlying hardware, the order in which these two elements of this array will be initialized may differ, and that will also result in they are getting different values. Okay, this obviously is at least one of them would be wrong, and that may lead to erroneous computation, leading to catastrophic failures. So it is this kind of non-standard methods of writing code that MISRA C basically tries to avoid. Then a list of various qualities, various standards, and these standards, as you can see, are aligned along certain high-level concerns, whether it is security, quality, sustainability, or data protection. Some of them are pretty familiar to us, I'm sure, right? And some of them may not be, but these are all highly adhered to in the automotive domain, and strict adherence is itself a billion-dollar industry. Certification comes very expensive, both tool-based certification as well as inspection-based certifications, and they are very highly valued in the industry. So these are the various trends that we see today. Okay, and then here is the model-driven engineering trend, and to represent that, I am talking about Simulink here. Simulink is a toolbox from MathWorks. Basically, it's a block diagram-based system design environment, which comes with a rich library of basic blocks, as you can see here. This is a very, very small subset of that, but what I'm trying to show you here is you can draw block diagrams of this kind by dragging and dropping this kind of blocks from the Simulink toolbox. After you are done with your, or after or during your modeling phase, you could actually do simulation, advanced verification and validation. And once you are satisfied with your model, you can do code generation with the press of a button. So this is a very well-used, well-utilized toolbox, Simulink. And there are many others like LabVIEW from National Instrument and so on, which are also very highly used. So there is a strong shift toward model-driven engineering. So here is the Simulink modeling process. I think this is sort of obvious. Let's move on. So these trends, it's not like they solve all our problems, and automotive software development is a solved problem. They in fact open up very, very interesting challenges, right? And some of them, a very, very small subset, completely driven by my own biases, are listed here. So we continue to be needing suitable computer languages for specifying and programming our systems. We also need sophisticated development environments which use those computer languages in a powerful manner, in an effective manner, and leading to high productivity of the software developers. We also need many quality assurance methodologies, particularly automated quality assurance methodologies. Okay, and in particular, we need tools to do formal verification for high-level quality assurance on high-level models. We need program analysis techniques to do static analysis or static checks on the program code. And then, of course, testing being the most important and most widely used quality assurance methodology, we need newer ways of testing our systems. So with that, I will move on to our part of the contribution. And hopefully discuss three, but I think I'm running out of time, so probably I will skip one of them. So I will discuss two or three of our contributions, which are basically aligned towards solving some of the challenges that we just saw in the last slide. So the first of our works is that on state charts. So this is a joint work with my PhD student Kartika, and contributions from a very large number of project students, most of them IIM students over several years. So what is state chart? State chart is basically a visual modeling language, very similar to Simulink, but it looks like state machines. It was proposed in 80s for modeling embedded systems. So very suitable for automotive software modeling. And already it has a large community of users, and several companies provide their own implementations of the same. It looks like finite state automata. So computer scientists easily take to this particular notation, but it enriches itself with action languages and hierarchy and many other forms of containments. Okay, so without going into the technical details, here is a typical model. Okay, a state chart model. As you can see, there are states here. These are states. Okay, and they are connected with transitions, with guards and action languages annotated over the transitions. You also see that states can be contained within other states. Okay, so fairly complex artifact, as you can see, and requires while it is very expressive, much more expressive than traditional programming language. It requires help from various tools to get it right. Okay, so what are the issues with this kind of modeling platform? Well, all the current variants of state chart, they have variables in their action language, but those variables have to be global. And in our understanding, this is a serious problem, because as you can see here, this is a very small state chart model. The actual state chart model in an automotive software would typically have anywhere around 50 to 100 states contained within complex hierarchies. And in that case, if you have to work only with global variables, it could be a work stopper in our opinion. It has got all the evils that global variables have for normal programming domain. Then there are other problems also. You may unknowingly introduce non-determinism. Your model may be such that it gets stuck in certain states, can't move out of them, or you may end up using variables which have not been initialized. So you need automated assistance to ensure that you do not unknowingly, inadvertently introduce this kind of bugs into your specification. And one of the things that we do in this particular project is basically that. So what we have done is we have created this language called Stable, which is a state chart based language. I would like to kind of cancel this out, because earlier we started that it would be for web apps, but we have seen that it is more suitable probably for embedded systems like Automotive. And one of the major things that we have done here is introduction of local variables. Okay, now that may sound like a very, very small little introduction or addition to the computer language of state charts, but trust me that that leads to all hell breaking loose. And because programming languages are very complex artifacts, it's very difficult to make their design modular, although you can create modular design using a programming language, but the programming language itself is very difficult to develop in a modular way. So there are plenty of feature interactions happening in the design of languages like state charts. So the moment I introduce locality to variables, it starts interacting with everything that you have in the modeling language, and that needs to be sorted out very carefully using rigorous mathematical techniques, to be proved experimentally, etc., etc. So that's where much of our efforts have been concentrated. We have developed an implementation of the stable language, a complete compiler which parses and type checks the models developed in this language and generates code in imperative programming language. And we have developed a number of specification and verification tools on top of that. So this is the summary of our first piece of work. So this is a stable model, a small one, but what I would like to show you here is the presence of local variables here. Okay, so these are all local variables to states. That's the thing that I wanted to show. And there I will stop with stable, and I will just have enough time to talk about one more piece of work, and that is about testing. So this tool is called SimTest. I've been working on it for over a decade now. It's a joint work with several collaborators, and primarily my PhD student Varsha. So the objective of SimTest is to generate test cases using a program analysis technique called symbolic execution. And the goal is to generate shorter test sequences. And we also have this notion of target edges, basically the edges in the control flow graph where we want the test execution to reach. Okay, so here is the architecture of the tool. I'll move on to this example. So this is the control flow graph of a system under test. Okay, and these red edges that you see here are the target edges I was mentioning. Those are the edges I want to reach. Okay, so we use a technique called symbolic execution to find a path which would take us there. And what happens is we often hit an unfortunate predicament called infeasibility of paths, infeasible paths. Okay, and which says that the path that we were about to go into turns out to be an unreal or infeasible path. And in such cases, we need to backtrack. Okay, so suppose I indicate that I want to go along this particular path to reach this particular edge, and it says that here is where I become infeasible. Then I have to take a turn, about turn, and probably go another way. Okay, and try to reach this particular place through another path. Okay, so this is what SimTest tries to do. Find a feasible path which takes us to the places we want to get to. Now, this has worked for some cases and hasn't worked for certain other cases. In particular, when SimTest says that we can backtrack by only one edge, which means if I hit infeasibility here, all I can do is to turn this way and try to get here through some other way. Okay, so this may lead to non-optimality as well as non-termination, and therefore we often need to backtrack by more than one decision edges. So here are all the decision edges, and I would like to consider the possibility of being able to backtrack by more than one decision edge. So our current efforts have actually been focused towards enabling SimTest with this particular property. So this is the overall architecture of our current tool, and what we basically do is we develop some sort of an experience from previous runs of the system and use that to calculate some probabilities and make a good decision as to where to backtrack to once we hit an infeasible point. So that is this particular method, and I think that's all I have to say about this. I had another section, but I will completely skip that. I'll go to the summary of my talk. So what I would like to conclude my section of the talk with is that the automotive software systems are very complex these days, no doubt about it. And that opens up lots of opportunities for software engineers, both in practice as well as in research, right? So software engineering in automotive sector is a very exciting research area, and I would definitely welcome collaborators and students to consider this as a preferred area of choice for doing research. So that's all from my side. I think before I sign off, I would like to mention, I'm now putting on my hat as the SIG coordinator. I'll just mention that next week we are going to have a talk from Dr. Ramesh from General Motors. He is a senior fellow of General Motors R&D, a very accomplished researcher. He used to be an ex-IIT professor, and now has been with GM for a very long time. And he's going to talk on software-defined vehicles. Currently, he is located in the Bay Area in USA, and therefore we have decided to shift the talk timing to 6 p.m. IST, which will be 5:30 a.m. For his time zone. So I would like you people to join us next Monday at 6 p.m. for Dr. Ramesh's talk. So with that, I would like to hand over the mic to my colleague Srinivas Vivek, who is going to talk about security engineering and automotives. Thank you.
Thank you, Professor Sujit. Let me share my screen.
Yes, yes.
Oh, great. Yeah, great. Yeah, thank you, Professors Roland and Sujit, for organizing Samvaad series on this very important topic. First, let me confess that I'm not really an expert on automotive security. Whatever I've learned in this topic is mainly because of many interesting discussions with Professor Roland Haas. And we don't have any research results, to present in this topic. So rather, I'll try to present the landscape and some important problems, and focus will be unfortunately only on the narrow part of intersection of crypto and automobiles. Okay, in spite of these limitations, I still think that I'll try to make the talk as interesting as possible. Great. So now we have seen that modern automotives, they have a lot of components talking to each other. So in particular, like we have communications between various components, within the vehicle, V2V, right? Or it could be from vehicle to the infrastructure, right? For example, it could be infrastructure could consist of the charging station, right? So vehicle needs to communicate with that. And it could be, V2X, means it can be a communication between vehicle to anything. Okay, for instance, cloud, maybe you want to run Alexa on your car, right? So there are a lot of entities communicating. Okay, for instance, automobiles, they could be connected via wireless networks, they can be connected to apps, many other electronic components and sensors, actuators, so on, right? So what is important to know is any communication between components. When we say that, like, we have multiple components, so now they are like external to each other, and they need to be securely, their communication needs to be protected. Okay, and then there's a good old saying in cybersecurity that a chain is only as strong as its weakest link. And now our chain consists of like hundreds of millions of code and possibly a billion line of codes in the near future. So the chain is really long, right? So, and then it can be, so it's not hard to imagine points where it can become very weak. So, and so adversarial scenarios, they typically may assume the worst case, right? And the hackers would try to attack the weakest part. So it's so important to protect the communication between various components. Okay, so in the picture you see another diagram of various components within modern automotive. And let me tell you briefly about two security incidents, okay, on real automobiles. So in the picture you see two security researchers, Charlie Miller and Chris Walasek. Okay, so from their laptops, at their homes, they are trying to remotely hack into a Jeep. Okay, that was driven by a reporter, okay, for Wired magazine. Okay, they could take control of the air conditioning, wipers, accelerators, brake, and ultimately they could just make the car crash. Okay, so glad that they were all coordinating. Everyone knew what's happening, but imagine what would happen if the hackers are malicious intent. Then it's going to be very dangerous. That's one incident. Another, more in the academic setting, but still real. The attack worked on a real automotive is by an attack by a company called Rescue. It specializes in security testing. It's based in Delft, the Netherlands. So what they did was they took out the dashboard of a car, and then they tried to inject a fault in what is called Unified Diagnostic Services Protocol. Okay, that's a protocol very commonly used in modern automobiles. Okay, so what is this fault? So by fault, we are not necessarily saying the fault, the bugs in software. It could be now what Professor Sujit typically addresses, but those faults can also be injected maliciously. For example, you try to run the clock underclock, or you overclock, make the system clock run at a lower frequency than, or at a much higher frequency, or introduce some voltage glitch. So, and then what you see on the right is a protocol for key verification. Okay, and if you can inject fault at the right place, it's possible they could show that this can be done, and then you just bypass the key verification step. So the implication is you give your car to servicing or during charging, and then they can just put some change the voltage and inject a glitch, and then there's no so without a key they can bypass key verification, and then without a key they can enter your car and then just connect it to everything what car is connected to, right? So this is dangerous. So these are the two settings I want to talk about. And then so what these things tell is we need to securely implement the cryptographic protocols. Okay, so cryptographic protocols are used to ensure security, but still we need to securely implement. So this is the storyline I'll be trying to convey in this talk. Good. So what is crypto? It's basically a set of mathematical techniques to ensure objectives of security, namely confidentiality, authentication, data integrity, non-repudiation, so on. Right. So you see the core of cryptography, and the basic problem what crypto addresses is secure and authenticated message communication. So that's the core of crypto. But nowadays crypto can do a lot more fancy stuff. And then what you see on the layer is crypto engineering, where you need to efficiently and securely implement. Okay, that's a topic in itself. I'm going to talk about that soon. And the bigger rectangle is the broad area of information security. So crypto is just one of the techniques to achieve information security. And information security, needless to say, has intersection with other branches of aspects of human life: economics, politics, social science, law, so on. Okay, so good. So crypto is important. We need to implement security, and we discussed that. Okay, confidential. We need to achieve confidentiality, of the messages communicating between various components of the automotive, and then and we should, so for that we'll just mention about encryption scheme. So what is an encryption scheme? As this diagram illustrates, so we have a sender and a recipient. So message that is sent on a possibly on a public channel means adversary could have access to the medium of which the message is communicated. So now, so sender, what he does is, he transforms a plain text on input a key. It could be a secret key for secret key encryption, or recipient's public key for public key encryption. So he enciphers into that plain text into what is called a ciphertext, and that is sent over the public channel. And the recipient on input his or her secret key can decrypt the ciphertext to obtain plain text. Okay, this is encryption. Okay, so encryption schemes are used to achieve confidentiality. So then how message integrity and entity authentication happens is via one of the important primitives is digital. They are digital signature schemes. So here a sender. So this is just like our hand written signatures. Okay, So only I should be able to produce, I mean, my signature, right? But anyone should be able to verify. So just like that, a sender, so we'll have a message, okay? And he or she will input his or her private key and create what is called a signature, okay? So that is given out, right? And anyone who have access to my public key, right? And anyone can access my public key will be able to verify, just like the handwritten signature. So this ensures authentication, data integrity, and entity authentication, okay? So signature schemes are used to achieve integrity authentication. So these two are the bare minimum crypto protocols that should be run on automobiles. Okay. So as I mentioned, crypto engineering is all about securely and efficiently implementing cryptographic primitives. Okay. For instance, so if we I mean, little bit in the future, if we talk about like smart junctions, smart cars, so the requirement is about, and again, communication between cars should be able, should be authenticated, right? Otherwise, I can, adversary can just, get access to the medium and send out like false messages, and so unauthenticated messages have no scope in, in all smart automotives or, whatever, right? So the requirement turns out to be about like 5,000 signatures, elliptic curve digital signature algorithm signatures per second per car. So that's a lot of throughput. And currently, the best software implementations can, only deal with about 1,000 signatures per second, unless we really get the hardware implementation, right? And that's going to be expensive. Okay, and the new dimension that is added to the engineering, the crypto engineering challenge is the real-time requirement. Okay, so we don't want cars to crash because the crypto runs slow, right? So these things are like, like they're quite like a massive challenge, and that, I guess, opens up a lot of venues for future research. So that's efficient implementation, we understand, but it turns out that that implementation should also not leak sensitive data. Okay, so here you see like a picture, a cartoon where an adversary is trying to listen to that observation. So typically, crypto is viewed as a black box. Black box. Something goes into the algorithm, something comes out, right? So plain text go in, and then ciphertext come out, right? Or in the case of signatures, messages go in, signatures come out. Okay, but it turns out that the adversary can get access to the the inner details. So for instance, it can try to measure the amount of time it consumes, or as the setups shows that it can even try to measure the amount of power consumed, for instance bank card, right? Or in the case of automotives, the charging stations. Okay, so suppose the car gets plugged into a charging station, and then you need to authenticate. So now it's much easier, if the adversary is control of the charging station, then it's so easy to measure the timing information, power consumption, so on, right? So then if there is some leakage of the secret key or sensitive variables through this, then the mathematical or the black box security of crypto primitives do not hold any longer. Okay, so for instance, what you see here is, so the decryption when it's happening, here is the naive implementation of RSA decryption algorithm. Okay, if we implement just naively, then it all just takes one power trace to find out the secret key, right? So wherever you see the peaks, it's all ones, and where you see a trough, it's all zeros. Okay, so and then within just one trace, without breaking all the mathematical challenges, you can just recover the secret key. So that's why it's so important to protect the crypto implementations and these side channel attacks. So before that, so what is important to notice, a fast implementation is not necessarily secure. This is what we should keep in mind while doing crypto engineering or security engineering in general. Okay, so how can we counter these side channel attacks? So basically, there are two approaches. So we try to make the leakage of the device independent of the intermediate variables. This is called a hiding countermeasure. Or we try to randomize the data, right? So to make it independent of the secret key, right? So this is called a masking countermeasure. So they all can be implemented in hardware and software. Hardware mainly because of high throughput, but again, they bring in significant overlay. So again, if we are talking about a billion lines of code, then it's going to be quite challenging. Okay. So these side channel attacks are passive attacks. It tries to learn, the adversary tries to learn the secret key. And as I mentioned in the scenario 2, the second security incident, so fault attacks are actually active tampering attacks. So you underclock or overclock, do a voltage glitch, or measure the electromagnetic emanation using a probe, or use highly targeted laser to inject precise faults. So it turns out that of using a faulty output is not just bad. You need to discard, but they can just reveal the secret key. So again, so this makes the scenario much more challenging. And there are countermeasures known to prevent against these fault attacks. But what is we need to keep in mind is they bring in a lot more significant warhead than the countermeasures against a channel attack. Right? So this is all I wanted to just briefly talk about security engineering, in particular crypto engineering, in the context of automotives. So I just need to I will conclude this part by saying that so this is an important topic, and then we need to incorporate the security in the design itself. No, it cannot be an afterthought. And then there are a lot of challenges and opportunities for future research in this topic. Okay. Yeah. Over to Professor Haas, please.
Yeah, thank you very much to Professor Sujit, Professor Vivek. I'll just, we'll spend a few sentences on summarizing our talk. So we have seen the major challenges coming from e-mobility, the shift towards e-mobility, autonomous driving, shared mobility, and the connectivity of the car. I have outlined how these challenges and how these trends will impact the overall system architecture of the car, especially the electronics architecture moving towards vehicle computers, high performance computers. The impact on the software part was then highlighted by Professor Sujit. He talked about the importance of software engineering methodology applied in this domain, driven by model-based approaches. And then there's a lot, of course, of research topics that come up, how you can formally verify and handle a complexity of up to 1 billion lines of code in the car and outside of the car. And all these connectivity and new features come with challenges in cybersecurity. That was then addressed by Professor Vivek. He talked about the car, its vulnerabilities through the networks, through the attack surface, and crypto engineering. That's a challenge. That is actually what needs to be done to design the efficient crypto protocols that actually enable cybersecurity in the car. And again, there are a lot of research topics and challenges there. So this field is also very fruitful. With that, I would like to end our talk and would like to hand over again to Professor Sujit maybe, or Professor Sujit for addressing the Q&A session of that, because I've seen that a few questions already came in to us as the speakers, and I'm happy to now lead over to the discussion.
Okay, so maybe let's start addressing the questions that have come up in the chat. So it is an invitation to all people in the audience to either type out their questions if they have one in the chat box, or they could raise their hands and come on mic and speak out their questions, whichever they prefer. In the meantime, let us take each question in order. The first one was from Shyam Murthy to Professor Haas. So Shyam, would you like to come on mic and speak out, or would you like me to read your question?
I can talk, sir.
Yes, please go ahead.
So Professor Haas, from the perspective of the automotive engineering perspective, from our institute point of view, what kind of research do you envisage students taking up in the coming future?
Mm-hmm. Yes, I think there are three very interesting domains from the application field. Let's start with e-mobility. E-mobility means the car is always connected, and we do have a lot of interaction between the car and the smart grid. So there are a lot of computational challenges in e-mobility that can be addressed. So several, research projects are there. There's a PhD on e-mobility, computational challenges. So there are domains here that can be addressed. And of course, e-mobility also has a cybersecurity aspect, like what Professor Vivek, outlined. We need the right crypto engineering protocols here, crypto protocols for cyber secure and fast communication in e-mobility. Other domain would be autonomous driving that needs the right methodologies from a software point of view, from a cybersecurity point of view, but also fundamentally AI, machine learning applications apply to this field. And although we have the first, on-premise experimentations there will be a lot of future research necessary to make it safe and secure. And the third area is virtual product creation, especially again with a focus on e-mobility, how you design the car and engineer it. It's a mechatronic device, so all disciplines come together. That is also interesting and challenging for IIITB because the focus is on computer science, IT, and electronics engineering. But here we have also the mechanical component, and we need the virtual product creation for a mechatronic system. There are best practices there, and the lab is coming up where this work can be done and research can be carried out. Yeah, just a few pointers from my side of research areas.
Okay, thank you.
Okay, so the next few questions are all from Srishti. So Srishti, I would request you to please come on mic and ask them yourself if possible.
Yeah, I read through, sir. So first question was in the context of the state charts. So I just read it. So the question is like this, that the state charts are state machine representations for any system. That's what I understand. And modeling on what level generally? I mean, components generally would be like, if I have to just visualize, what kind of modeling can I do? If some comments on that. And
so, okay, fine. So shall I take the sub questions one by one? Or?
Yeah.
Okay. So state charts can be used at various levels, beginning from as high as the requirement analysis level to something as low as the detailed design level. So we have seen state charts being used at all levels. For example, take the simple lexical analyzer of a compiler, right? It's a specification of the lexical analyzer, but then the code itself is a state machine in that sense. So state machine formalism is extremely robust and versatile way of representing object life cycles, and it could be used at any level of software development life cycle. That's my this thing. And also it can be used not necessarily for a particular domain. I have seen it being used in various domains, ranging from cyber physical systems all the way to enterprise applications.
So basically, wherever there is a state machine design underneath is where this can be used, right?
Not necessarily state machine design, but wherever there is the need for visualizing the life cycle of something. So state machines are life cycles of something. It could be a process, it could be an object, it could be anything.
Okay, understood. So I think the next one was also in the same line. One was that, so this doesn't has any language orientation, or since you said it can also be used at the implementation level. So from the design, can we also export out something which can directly be used? Are such visions also around this tool?
Actually, this is already in the practice. So if you consider, I mentioned Simulink, right? So there is a toolbox called Stateflow, which is part of the Simulink toolbox from MathWorks, and that's where you can do state chart modeling. And there are all the other things from IBM Rational, etc., etc. All of them come with code generators, which means that you model using state charts, and then generate your code with a press of a button. And the action code that you embed inside your state chart model, the various vendors, the various flavors allow you to choose your favorite language. It could be C, it could be C++, it could be Java, or any of the many other programming languages available. So in that sense, it can integrate with a variety of other subsystems.
Actually, some of these tools is what I have also used, but I also wanted to understand that how do we outline the scope of this tool? And also, my next question that also follows in the same line, is there anything specific wherein we can say that this tool can be used in embedded systems? This question, there is a background to this question, because usually when we do development in the embedded systems, we see that not all these tools is what we can right away use when we write low line of codes. So you can do it at some top levels, but situationally in the embeddeds, when you come, you have a lot of other nuances to be seen. So this tool doesn't help you directly. So I also wanted to understand, is there something very specific to embedded system that also has been taken care or suggested? Any comments on that for this tool only?
I think so your question is actually very loaded. I can understand that there's a lot of experience behind what you are asking, but the immediate answer to that question, short answer, is that there is no formal reason that why embedded people use it more. But the answer could be found in the fact that embedded systems are often safety critical. They require certain amount of mathematical rigor while you are designing. Okay, and therefore there is a propensity or tendency among embedded software engineers to try and mathematically model their systems. It could be algebraic equations, or it could be finite state representations and such things. So I think the answer, as I said, it's more of a practice driven thing. So since people are looking for more abstract representations of the systems they are implementing, that's where formalisms like state charts come in. But having said that, I completely agree with you that we should not try to fit in force fit everything into a state chart modeling way. That's not the idea.
Okay, understood, Professor. I think just in continuation to that, on the topic of sim test, there was another question. So this question is like this: what we are attempting to do with the sim test, is it also not falling in line with the static analysis and the dynamic analysis tools that also gives us similar clues for the software developments? So
yes, so this is an automated test generation tool, and obviously automated test generation is a very examined area of research. So it is not the first in the line in that sense, but the techniques that it uses and the results that it achieves have certain novelty about it. So the idea of automated test generation per se is not propounded by sim test at all.
Okay, understood.
Yeah.
I think after this, there's one more query that's going for the crypto engineering.
I think we should give you an award for being a very ardent audience, active listener.
So just last question in this line is, this is in context of crypto engineering. So the question is like this, that how much security, why I'm asking this, because how I see this crypto engineering system is also a solution that we have brought to bring in security, but that itself needs some sort of security. So on that line, exactly, I just wanted to have your comments.
Yeah, sure. Yeah, so security, it's possible to quantify it. So we typically quantify it as like how many bits of security is assured, like 80-bit security or 128-bit security. So it means that how many primitive operations the adversary needs to perform in order to break the security objective. Okay, so it's possible to quantify, right? But then see, I understand that, the way I presented, it seems that, okay, the security protocol itself needs to be secured. So, but there are, why I mentioned is because historically, all the crypto primitives, they are viewed as black boxes. Okay, I told, right? Something comes in, something goes out. So it's only like past 25 years or so, we have been looking into the attack surface. The researchers, they are incorporating the wider attack surface where implementing security, but there are a lot of, quite rigorously analyzed models that incorporate these side channels, and then your constructions are also, sort of like you can formally analyze or formally argue about its mathematical security in the extended models that also consider implementation-based attacks. So not that we don't have solutions, but it's just that the automobiles, they present like grand challenge in terms of real-time requirement on the huge complexity of the code. So these are the challenges. So,
okay, maybe I can understand this part like this, that let's say using the crypto engineering, we can bring in, let's say 60% of security in the entire system, and then 20% is also going as an effort to secure this. So still,
no, not really. See, not really. We cannot. So it can provide 100% security in whatever sense, in whatever sense it makes. But it's just that it needs to be incorporated. Not that there aren't solutions. It's just they need to be efficiently adapted. That's all.
okay, okay, yeah, fine. Thank you, professors.
Thank you, Srishti, for your questions. Any other questions from the audience? Okay, if there are no immediate questions, may I ask one question to my co-speaker, Professor Roland. Roland, what is the current trend in terms of so my question is somewhat similar to one of the first questions that was asked. If we were to design our pedagogy to address the requirements of the automotive software market, can you give us some top level suggestions that come to your mind as to how we should maybe adjust our pedagogy or our curriculum so that we have ready workforce for our automotive sector few years down the line? Hopefully it's not a very trick question.
Yeah, I think it is very important that there's a fundamental understanding of the vehicle and its context. What are the challenges coming from this domain? We talk about the mechatronic system. We talk about the system that needs this connectivity. We have then this AI, machine learning, new features in the car, and the context in the car, in its smart city environment. It's also very important. From that, we derive certain requirements that will play a role also for the curriculum to understand this very complex mechatronic systems, and then how we can relate to the best practices and methodologies that are being trained in the software domain, in the electronic domain, in the basic computer science domain. And this challenge, this translation between this real life automotive engineering and the curriculum, that is a challenge. You see that, for example, with certain things, how modern cars are being developed, what's the lab infrastructure you need for that, or to lay your hands on a real car to experiment with that. That is something that maybe in the future would be very nice for the students to see, so that they can transfer what they see in the field into their curriculum, and then also see how this best matches.
Thank you, Roland. Thank you for the answer. So if there are no more questions, then I would like to close this session by formally thanking all the speakers, Professor Roland, Professor Srinivas, Vivek. Thank you, everyone.